right, we are ready to look at section 5.2, which is on a topic called definite integrals. Make sure your cell phone is put away and out of sight so you can focus on this for the next few minutes. It's a fairly short video. What I want to remind you to begin with is that in the previous couple of sections, we looked at estimating the area underneath the curve using these rectangles, which are also called Riemann sums. And we saw early on that the more rectangles we include in our estimate, the better our approximation. The more our approximation becomes, or the closer our approximation gets to the actual area under the curve. And I don't know if we've seen this notation yet or not, but the sigma notation, I know we talked a little bit about sigma means sum, and one way to write this is the sum or the sigma of each individual rectangle. So this is the sum of the area of each rectangle. And the idea is that we want the number of rectangles we're using to get bigger. We want more and more rectangles. So what we would do is we would say we want the limit of n, if n is the number of rectangles, we want the limit as n approaches infinity for the sum of all of those areas. And we're not going to do a lot of these by hand, but I want you to just sort of be familiar with this notation and know that this is also known as the definite integral of the function f over the interval a to b. And later on, Leibniz, the mathematician Leibniz, we've heard of him before. He's the one who came up with Leibniz notation for derivatives. He came up with a simpler notation for writing this definite integral. So instead of writing the sigma notation every time, he used this notation. We have seen that before, that integral symbol of f of x with respect to x. Remember that that was the antiderivative. We did that back at the very end of chapter 4. So the antiderivative of little f of x. That notation we've seen before. What's new is that we're adding these limits of integration from a to b, and that gives us what's called the definite integral. So this represents basically the area underneath the curve of f over the interval from a to b. We're going to learn a couple of techniques in this lesson to help us make the evaluations for these definite integrals. So look at example 1. It says make a sketch and you evaluate this using geometry. So what I want you to notice is this is the function y equals 2x. Let's make a quick graph of that. That would be a linear function with a y-intercept of 0 and a slope of 2. So we're going to go up 2 and over 1. And what the definite integral tells us is that we want the area bounded by the curve and the x-axis rather over the interval from -2 to +1. So I'm going to shade that in. We're looking at this little triangle region down here. Label that again, and then this triangle region up here. So we can use geometry to figure out what these two areas of these triangles are. Remember, the area of a triangle, of course, is 1/2 base times height. So for the first triangle, we would have 1/2. The base would be 2, and then, so this distance here would be 2, and then this distance in this direction, well, if you substitute 2 in for x, you get -4 for the corresponding y value. So the height would be 4. So that would give me 4 for the area of that triangle. And then on the other side, we're going to do the same thing, but the base is 1 and the height is 2 going this way. So my area there would just be 1. And one thing we'll talk about in the next little page here is that if we are looking at a region that is below the x-axis, when we're working with the integral, then that's going to be negative. So let me show you what I mean. The value of this integral from -2 to 1 is going to be equal to -4, because this part, The area was 4, but because it was below the x-axis, we're going to make the integral value negative, plus, and then we're going to add up the area of the positive part. That was 1, but because that's above the x-axis, we're going to keep it positive. So my final value for this integral would be -3. Now this question makes use of a few properties that we're going to get into a little more down here, but note that this says if f is continuous and non-negative on the closed interval, then the area of the region bounded by the graph of f, the x-axis, and those vertical lines is given by that integral. So the integral itself could be negative if we're below the x-axis, but they're saying here if this is non-negative, if the function itself is non-negative, we simply look at the area. This is not as complicated as it sounds. We'll get into some of these properties and you'll see what I mean. Look at example 2. It says write the integral that represents the area under the curve for this function from 0 to 4. So the area under the curve is going to be the integral from 0 to 4 of the function itself, 4x minus x squared, and then the dx needs to go at the end. And that's it. So this represents the area of that pink region. All right, a few properties here that I was talking about. The first one says the integral from a to b of a function is equal to the negative of the integral from b to a. So we'll see from time to time where that will be helpful. The second property says the integral from a to a is just 0, which I think intuitively should make sense because if you don't go anywhere, you're just a to a, there's nothing underneath the graph. So that would just be 0. The third property we did when we did indefinite integrals back in section 4.9, but it says if you're multiplying by a constant, you can put that in the front of the integral, if that helps you. The fourth one is the same. We talked about that previously, and actually this says plus. It really should say plus or minus, so make sure to make that correction if you need to. But you can separate definite integrals just like you could indefinite integrals. Number 5 says the integral from a to b plus the integral from b to c is equal to the integral from a to c. Now we actually use that property back here in this example. Let's talk about that for a minute. What I did is I said the integral from -2 to 1 for this function was equal to the integral from -2 to 0. That was the first triangle that I worked with on the left side, plus the integral from 0 to 1. And that was the second triangle on the right side of the y-axis. And that property is what I used to break that up. So that'll come up a lot. Number 6 says if f is non-negative and integrable, then the integral from a to b should be positive. And of course, if f is negative, then that integral value will be negative. Again, that's what we saw back here with this example. And then finally, if f of x is less than or equal to g of x in a given interval, then so too will be the integral of f from a to b versus the integral of g from a to b. Some of these sound more complicated than they really are. So in class tomorrow, we'll do some examples where we'll apply these different integrals and you'll kind of see how we'll use them to help us solve some problems.